Alright, welcome everyone to 3.6. This is the final section in Chapter 3, Derivatives, an algebraic viewpoint. So instead of coming at this from a numerical or a graphical viewpoint, again looking at graphs, trying to figure out what the derivatives are, or looking at tables or calculators, we're going to try to use algebra in this section to calculate out some derivatives. So in order to actually use some algebra, it'd be useful to have, kind of a more formal definition of what the derivative is. So that's this very first part, the 6.1, the derivative of f of x at a is given by this formula here. And the claim is this is essentially what we've already seen, right? Last section in 3.5, we talked about between these points, right? We had this p being a and f of a, and q being a plus h, comma f of a plus h, that the derivative was given by the average rate of change between these 2 points, letting h go to 0. So if I was to calculate out the average rate of change of these 2 points, right, so that's going to be the change in y values, so that's going to be f of a plus h minus f of a, divided by the change in x values, so a plus h minus a, and you can see, let's see if I can get my red pen out, that we get a little bit of cancellation here, and all that's left is h on the bottom. So that's where this formula comes from. And then, as we mentioned last time, we want h to be very small. We want h to be going towards 0. And that's where we're going to be using our limits, our information from 3.1 to actually calculate these things out. Now this is very useful, and it's good to be able to find a derivative at a specific point. But what's even more, I guess, impressive is being able to figure out an entire derivative function to try to figure out the slope at every single point. And therefore, it's nice to have the second definition, which is a claim is it's exactly the same, or pretty much. So this says the derivative function. So the derivative, and then you get to specify which x value, is equal to the limit as h goes to 0. So same sort of setup here. And now f of x plus h minus f of x, all divided by h. So essentially you can see everywhere you see an a, you're replacing it with an x. An a here, you replace it with an x, and that's all there is to it. So that's why I said it's pretty much the exact same. Okay, so we're going to be calculating out some derivative functions, and that's going to be really powerful here. I'll show you an example in just 1 second. The last thing that I wanted to bring up is this thing, this Leibnitz D notation. So later in the class, and in other calculus classes, you'll find that we really need to specify what you're taking the derivative with respect to. So this little prime notation right here doesn't really say so much what you're taking the derivative with respect to, right? We know that we're taking the derivative with respect to x in this case. But later on, it may get more confusing, right? So it's nice to have this type of notation, and so let me give it to you here. So the Leibniz notation for f prime of x is going to be equal to dy over dx. Right, and kind of I have below here, this makes a lot of sense since the derivative is a slope. Slope is supposed to be given by a change of y divided by a change in x. So you can see that this d, you should think about it as a small change. A small change in y, a small change in x. So this is what the slope looks like. You may also see that this is sometimes written as df dx, right? Because again, y and f seem to be more or less interchangeable here. So you may see df dx. I don't like this one as much, but it does come up in the book and stuff. And then it's a little bit more of a pain, but you can express the derivative at a specific point. So like, for instance, f prime at a specific point a, this would be dy dx, and then you have this long bar right here, which means evaluated at x equals a, and then this x equals a is a subscript right here. So the derivative evaluated at x equals a. And again, you may also see this as df dx, evaluated at x equals a. So this is maybe the drawback of the Leibniz D notation. And just as a quick note, whenever we have a name and stuff, I like to know who this guy is. So here he is, Leibniz, Gottfried. He's one of the founders of calculus, essentially. Him and Newton more or less co-founded calculus independently of one another. So he was born in the 1600s, died early 1700s, age 70 or so, and he's German. So I guess really Leibniz, there you go. So, okay, so that's who Leibnitz is. And that's the D notation. Okay, so as promised, let's actually try to use this definition to calculate out something. So here we are. We have f of x is 3x plus 1, and I want to calculate the derivative function. So in this case, I'm going to go back to my definition. So my definition for f prime of x is the limit as h goes to 0 of f of x plus h minus f of x all divided by h. So the limit as h goes to 0. Okay, so first thing, f of x plus h. F of x plus h, well, that's just like f of x, but everywhere I see an x, I'm going to plug in x plus h. So this is going to be 3, and instead of x, I'm going to put x plus h plus 1, and now minus f of x. And this is a common mistake right here. Let me show you. I'm going to put 3x plus 1, just like this. And so the common mistake is that, let me maybe get out a green pen, that you need to subtract away all of f of x. So you subtract away all of f of x. But I only subtracted away the first part right here. I'm only subtracting away the 3x. So I need to subtract away all of it. So you need to include brackets or parentheses or something to make sure that you're subtracting away all of it. Okay, then we're going to divide by h. And so let's go ahead and try to simplify some of this stuff. So maybe first I'm going to distribute the 3, I'll distribute the negative sign, and see what we get. So that's going to be 3x plus 3h, the 1's all by itself, and then minus 3x minus 1, all over h. And so you can see already that there's some cancellations that's happening here, right? Plus 3x minus 3x, plus 1 minus 1. And so what we have left is the limit as h goes to 0 of 3h over h. Ah, well that means that these h's now cancel, right? Because everything on the top has an h, everything on the bottom has an h, so they cancel. And so this is just the limit as h goes to 0 of 3. Well, there's no more h, right? So you can go ahead and just use this direct substitution property, really. But there are no h's. So the answer is just 3. And so the claim is this makes a lot of sense, right? So back when we were originally thinking about the derivative, right, this is supposed to mean slope. So the slope of this function right here is 3, right? So, and it doesn't matter what the x value is, the slope is always 3. So this in some sense was a silly case, but I think it's nice to be able to see how do you actually apply this definition of the derivative. Okay. Let's go ahead and move on to a little bit of a less silly case, something a little more standard that you might see. So this was from last time. In 3.5, we had this example 5.4, which was 1 minus x squared, and we were approximating the derivative at 3. So I'm going to do this now algebraically. First, I'm going to find f prime of x, and then I'm going to use that to find f prime of 3. So I'm going to show you kind of how the derivative function is very, very powerful, actually. Okay, so let's get to it. Again, my derivative formula is going to be the limit as h goes to 0 of f of x plus h minus f of x all over h. Here's my f of x function right here. So my first thing is to find f of x plus h. So everywhere I see an x, I'm going to put an x plus h. So 1 minus, and instead of x, I'm going to put x plus h. Okay, minus, and remember I need to subtract away all of f of x. So here is my f of x right here. I need to subtract all of it, divided by h. Okay, limit as h goes to 0, and now it's a little bit of algebra time, right? I promised you there was going to be algebra here. Let's go ahead and try to expand this. And remember, let me put this in red. When you have a quantity squared, you can't just distribute like this, right? That would be very, very bad. You have to remember that there's technically some foiling going on, that this is x plus h times x plus h, and so you need to do firsts, inners, outers, and lasts sort of deal. Okay, so if I did all that, the first, inners, outers, lasts, I would have x squared, that's my firsts. My inners would be hx. My outers would be, again, an x and an h, so I'm going to write hx. And then my last would be h squared, h times h. Okay, so yeah, you have to be very careful about that. You can't just distribute that squared. That would be very, very bad. You would not get the right answer. Okay, so let's go ahead and write down 1 minus x squared plus, okay, so I have an hx and another hx, so I'm going to write 2hx plus h squared. Notice how I still have this this minus sign, and I need to distribute that to all of it, right? That's where that comes from. All right, minus 1 and then minus a negative, so plus x squared. All right, all over h. So this is going to be the limit as h goes to 0. And let's go ahead and distribute this minus sign now. So I have 1 minus x squared minus 2hx minus h squared minus 1 plus x squared. And now we can see that there's some cancellations that's going in on the top, right? So plus 1 minus x squared plus x squared. So those all go away. And so I have the limit as h goes to 0 of negative 2hx minus h squared all over h. And you can see now everything on the top has an h and everything in the bottom has an h. So I can go ahead and cancel 1h here, 1h here, 1h here. Technically there's a 1 left in the denominator. And so that's going to give me the limit as h goes to 0 of, let's see here, this would be negative 2x minus h. And so now the limit as h goes to 0, right? There's no problem of me just using the direct substitution, right? I can just plug in a 0 everywhere I see an h. And when I do that, I'm going to get negative 2x. So that is the derivative function. That is my f prime of x. So if f prime of x is equal to negative 2x, then f prime at 3 is going to be equal to, well, just plug in a 3 everywhere I see an x, and that's going to be negative 2 times 3. That's negative 6. Let's go back and check really quick. Way back up here, when we were first doing these things, I wanted to approximate the derivative here, f prime of 3, by calculating the average rate of change over small values, and we saw that, yeah, it was very close to negative 6.01, negative 6.001, and we said it's probably negative 6. It's, I mean, you know, we can't be certain, but I mean, that's the only thing that's really close to it. It makes sense that it would be negative 6. Now we can exactly say it has to be negative 6, right? Using this. Okay, the last thing, find the equation of the tangent line of f of x at x equals 3. So this is going to be using this formula that I gave you. One more time here. Theorem 5.7 gives us an equation for a tangent line. So that's what I'm going to be using in order to write down the equation of the tangent line. So let's go ahead and do that. So the equation of the tangent line is going to be y minus f of a equals f prime at a times x minus a. So in this case, our value that we're pinning this to is 3, right? That's our a value. So this is going to be y minus f of 3 is equal to f prime of 3 times x minus 3. Okay, well, I just did a lot of work to figure out f prime of 3 is negative 6, so I could go ahead and plug that in. And then the only thing that really is left is what is f of 3. So let's go back up here really quick and say f of 3 would be equal to 1 minus, okay, 3 squared is going to be 9, so that's going to be negative 8. So minus negative 8, so that's the same thing as plus 8. Now I would accept this for full credit, but I understand you may want to try to simplify it down. You certainly can, right? So then it would be y plus 8 is equal to negative 6 plus 18. Oops, see, I already made a mistake. Negative 6x plus 18. So that's me distributing this negative 6 right here. And then let's subtract 8 from both sides. So that's going to be negative 6x plus 10. So if you'd like to, you can do this. Okay? Okay. the last piece of information I have you, I'd like to kind of give you this example to illustrate it. So first thing, I'd like to sketch a graph of, the absolute value function, right? So part A, sketch a graph. So whenever I don't know how to sketch a graph, right, I go back to the point plotting method. So if I was to plug in, for instance, 0. If I was to plug in 0, well, the absolute value of 0 is just 0. If I was to plug in 1, right, the absolute value of 1 is just 1. How about if I was to plug in -1, right? Then absolute value of -1 is still +1. So again, I'm just plugging in different x values and figuring out what the y value should be. So in this case, if I plugged in -1, I would get out 1. And if I plugged in 2, I would get out 2. If I plugged in -2, I'd get out 2. And so you can see it's looking something like this. I think these are going to be fairly straight lines here. And now it's nice to use our calculators to double check. So let me go ahead and pull out our calculator. And I actually did this a little bit earlier, but let's go ahead. There's an absolute value function that you can do, and this is under math. And then you go over to the num tag for number, and then ABS, this is absolute value. So ABS, and then I'm going to do of x. So ABS of x, enter, and I'm going to hit the graph button. And yep, so it looks like this nice V shape. Right, so there's our absolute value function. So now based on the graph, right, now we're on B, based on the graph, what is f prime of 1? So what is the derivative at 1? So again, using this graph here, if I'm interested in what is the derivative at 1, again, we're thinking about slope. Slope at a point, the instantaneous rate of change, stuff like this. So if I tried to draw, a line here, well, you can see it models this line pretty well, right? So this slope at a point, I would guess, is 1. So I would say f prime of 1 is equal to 1. But actually, I wanted to show you a trick on our calculators that we can do. So if I pull out my calculator here, under calc here, which means calculate, so second trace, there's an option for dy dx, which now we know this is the Leibnitz d notation. So let's go ahead down to that for the derivative, right? So I'm going to calculate the derivative, and then it gets to specify which x value. So I'm going to go ahead and type in 1. So if I click 1, and then I hit enter, it says dy dx is 1. So this verifies, right? At x equals 1, the derivative is 1. So this is a nice trick that we can use in our calculators to figure out the derivative at specific points. Now notice you cannot use this to figure out the derivative function, right? It's not going to give you the derivative function, but it will give you derivatives at specific a values or specific points. Okay, now this is really why I wanted to bring this up. For C, based on the graph, what is the derivative at 0? And so if I was to use my calculator here, let's bring that up, and do second trace to get to calc, and go down to dy dx, and I want to know what is the derivative at 0. So I'm going to hit 0 and then enter. It says dy dx is equal to 0. And interestingly enough, our calculator is wrong. It's very rare for a calculator to be wrong, but in this case, it very much is. So, why is it wrong? So the answer is not 0. The actual answer is that this thing, f prime at 0, does not exist. So remember, this derivatives come to us from limits. We need a left-hand limit and a right-hand limit. So if you were to try to figure out what is the slope at the point, what are the derivatives of all these values that are just a little bit bigger than 0, right? The slope at a point here would be 1, 1, 1, and the slopes at the points over here, a little bit to the left of 0, right? These are all probably -1, right? So the slope is negative. But so our rise would be -1, our run would be 1. So yeah, you can see all of the slopes are -1, -1, -1, -1, because again, these look like straight lines. So in this case, when you take the limit as you approach from the right, you're looking like 1, 1, 1, 1, 1. Versus if you approach from the left, you get -1, -1, -1, -1, right? So therefore, the left-hand limit and the right-hand limit do not agree. So remember that the derivative is a limit, so we need the left-hand limit and the right-hand limit to agree. So this is a pretty special case, but sometimes the derivative does not exist. So that's an important topic that I wanted to make sure to hit with you on these videos, and we'll talk about it a little bit more in class. Okay, so the last thing here is a nice definition to kind of relate to this. So in the above example, we see that the derivative does not always exist. In this case, we say f of x is not differentiable at x equals 0. So not differentiable means the derivative does not exist. Okay, so that is the end of the video and the end of chapter 3. I'll see you guys in class. Adios.